Welcome everybody to this next event in our external speakers series. Today we have Professor Sean Carroll, who's a professor of physics at Caltech and a fractal faculty at the Santa Fe Institute, soon to be joining Johns Hopkins. Sean also has done a lot of work on quantum mechanics as one of his main research fields. So this is also a great kickoff event for next week's workshop on quantum causal models. And you might think about this when we get into the Q&A later on. Maybe we can tap into that. On your website, it says you're interested in how the world works at the deepest levels. So I think it's quite natural that you're drawn into causality research, and we're very welcome to hear you talk about the era of time in causal networks. So please join me in welcoming Sean Carroll.
I'm trying to think, this might be the first talk I've given at a university since the end times began. So it's good to be back and speaking with people in a real audience, etc. Just to manage expectations, there will be no quantum mechanics in this talk whatsoever. I do know some quantum mechanics, and I'm happy to answer questions about it, but this is very classical. And actually, I know very little about causality. I know that the people in the audience who are engaged in a program doing research in causal networks and so forth. This is not my area. I'm trying to learn about it. So I'm hoping to learn from you during the talk. I am in some sense an expert in the arrow of time and entropy and the physics behind that. So I'm going to try to connect these two areas, hopefully in ways that will be useful. And this is one of these questions, the arrow of time and causal networks, where it's not like we're basing our major results on some heroic technical calculation. The actual equations are pretty simple. It's really a matter of asking the question in precisely the right way. So what is the question that we have in mind? Here's what I take to be a standard question that we ask in the world of causality. Is it true that smoking causes cancer? Or is there some other confounding factor like a genetic predisposition that causes both smoking and cancer? For those of you who are not experts in causality, you might think we know the answer to this, and we do. Smoking causes cancer. But in the 60s, it was not hard to find people who you could pay to say that maybe genetics caused both of them, and it was not the actual smoking that was causing the cancer. So how do you know? What you know is that there's a correlation that people who smoke get cancer, but maybe if something else is causing both of them, stopping smoking would not lower the incidence of cancer. That's the question that is addressed, a kind of question that is addressed by causal analysis. Here is a less common question that you could address. Does smoking cause cancer, or does cancer cause smoking? Very few people ask this kind of question because there is a subfield or a part of causal analysis called causal discovery, where we ask about the directions of arrows in these pictures. So these are Bayesian networks or causal networks or whatever you want to call them. We have some random variables and they are described by a joint probability distribution. And these arrows, it's a little bit harder to exactly explain what the arrows are, but informally, intuitively, they're supposed to tell you that at least potentially this variable can have a causal effect on that variable, okay? And usually, if it's something like smoking and cancer, you presume from the start that you know that cancer doesn't cause smoking. It comes after. There's no mechanism you can think of. So you draw the arrow going from smoking to cancer without thinking about it too much. And the hard work is done asking if there are other arrows. But this question, to those of a more philosophical bent, is kind of interesting. How do you know exactly in what direction to draw the arrows? In particular, a well-known fact about causal influences in the world is that the cause comes before the effect. We can argue about that one too, but as a general rule, that's the way it goes, directed in time. And so the question is, why is that true? And this is not, as far as I can tell, maybe you can correct me if I'm wrong, but from trying to read through these things, this is not a commonly addressed question. In fact, it's the opposite. When you look at methodologies of causal discovery, one of the rules you're told is if something happens before something else, the arrow has to go from the thing that's happening first to the thing that is happening second. So you're not deriving that fact, you are postulating that fact when you're drawing your arrows in the first place. I want to know how to derive that fact. Why is it true that in the world, what we identify as a cause always comes before what we identify as an effect? Well, This is clearly an aspect of what we call the arrow of time, right? The fact that the past and the future are different in various ways. If I show you two pictures of somebody sufficiently separated in time, I don't have to specify which of these pictures is earlier and which of these pictures is later. You just know, right? There are certain things that happen in a very predictable way, in a very clear directionality to time. We remember the past and not the future, right? We have records of the past. We have photographs, fossils, history books. You can try to predict the future, but you do not have an artifact here in the present day that specifies some particular thing that is happening in the future that could have happened otherwise, like someone's birthday being a certain date or someone having a certain incident in their past, etc. Biological evolution, personal aging of organisms, and the cause and effect arrow. These are all examples of the arrow of time. And if you were living 2,000 years ago, 2,500 years ago, if you were Aristotle, a friend of Aristotle, lived in that world, this would not have been a question. You would not have wondered about the arrow of time because it was just obvious. The past and future are different things. Like, why should there be a surprise in the fact that there's an asymmetry between the past and the future? The present is what exists, if you're a presentist, if you're 2,500 years ago. And the past is something that happened in the past. It's fixed. The future hasn't happened yet. It's up for grabs. So it's obviously a totally different kind of thing. Then along comes physics and throws a spanner in the works, as it often does. Ever since Newtonian mechanics, our best guesses at the fundamental equations of physics have had the property that they don't distinguish between the past and the future. They treat the past and the future the same. And there's, again, many different manifestations of this or ways to talk about it. Here's just one, the equation that governs in Newtonian mechanics the evolution of the orbit of one object around another. Here it is. The second derivative with respect to time of the position is given by Newton's inverse square law. And what you notice is that you don't need to understand all these symbols. They're not that hard. But if you send time to minus time, if you reverse the direction of time, in this equation, time only appears once, and it appears squared. So if you send t to minus t, this equation is unaltered, okay? So that is a symmetry of the dynamics. The fundamental rules of Newtonian mechanics work the same running forward or backward in time. Another way of saying that is if you made a movie of one object moving around another one, and you played that movie to another person, but you played it backwards, they would not notice anything funny, okay? If you have a pendulum rocking back and forth and you make a movie of that, play it backwards, it looks the same. That's a manifestation of the fundamental reversibility. There is no arrow of time deep down in the fundamental laws of physics. And this remains true when you invent quantum mechanics and the Schrodinger equation, relativity, or anything like that.
You got a wrong factor of m there. Equivalence principle.
You're right, I do. They're going to revoke my physics license. They're going to call me a philosopher now. But yes, you're right. There should not be a little m there now that I think about it. Okay, sorry, thanks. I told you, Patrick, we should not record this. I told him we shouldn't record it. All right, this is evidence I made up these slides on the car ride home. Okay, here is why we do have an arrow of time in the world. The arrow of time is not fundamental, but it is there in the emergent larger scale world, the macroscopic world in which we find ourselves because of this rule, the second law of thermodynamics. The second law of thermodynamics, the first law just says energy is conserved, no big deal. The second law says that entropy increases. We'll get to what entropy is at a technical level in a minute, but roughly speaking, it's a measure of the disorderliness of something, the randomness, the disorganization. This is not the ideal picture, but it's a pretty picture of the evolution from an unbroken egg to a broken egg to scrambled eggs. Disorder is increasing, entropy is increasing, and this happens, again, if I made a movie of breaking the egg and turning into scrambled eggs, you would know if I played that movie backwards, right? You don't see movies where you take the scrambled eggs and turn them into an unbroken egg. That doesn't happen. There's a pronounced directionality to this macroscopic phenomenon because entropy is increasing. So what I want to claim is, I haven't explained this phenomenon in detail yet, but I'm going to claim that the only reason there is an asymmetry between the past and future in the world is because entropy is increasing over time. And therefore, if there's any other phenomenon that you know about that indicates an asymmetry between past and future, it is ultimately because entropy is increasing. And that includes the fact that causality has an arrow of time. So we should be able to trace the fact that causes precede effects to the fact that entropy is increasing over time. And so that's the claim. The reason why there's causes precede effects is because entropy is increasing with time. The thing to note here is that you know both the starting point and the ending point. The starting point is that entropy is increasing. The ending point is that causes precede effects. It is famously hard to figure out how to connect correctly the beginning point to the ending point if you know both of them. It's not like we don't know the answer yet and we're looking to find it. We know what the answer is. Causes precede effects. So there are many wrong ways to get the right answer. There are many ways to trick yourself into thinking that you have established the connection between these two things. That's what we're trying to figure out. So I think maybe we can make some progress there, but maybe you disagree. We'll find out. Here's the example I want you to keep in mind, not from any personal experience, but sometimes people knock over glasses of wine and they fall on the floor. Okay, you may have seen this happen in the world. So to formalize this, we're going to set up a set of random variables, X, Y, and Z. And the random variable X is that at 7 o'clock, AM or PM, I presume it's PM, but I don't judge. I don't know what wine o'clock is in Berkeley. I either swing my arm or I don't. That's a 1 bit worth of information, random variable. At 7 o'clock plus 1 second, the glass falls off the table or it doesn't. And at 7 o'clock at 2 seconds, there is wine now on the floor or there isn't, okay? These are the 3 random variables and they're correlated with each other in the real world. In fact, to make things simple, we're gonna assume the correlations are perfect. So in other words, if there is no wine on the floor at 7:02, then I did not swing my arm and the glass did not fall. If there is wine on the floor, then I did swing my arm, the glass did fall with probability 1, okay? So it's not like likely, it's 100, not just likely, it's 100%. What you notice about that is that, and we'll come back to this, but this joint probability distribution for the 3 random variables is entirely symmetric with respect to time, right? If I tell you at 8 o'clock that there was wine on the floor at 7 o'clock plus 2 seconds, you know with certainty that 2 seconds earlier, I swung my arm, okay? I'm assuming this is true. I'm not deriving it, but let's imagine that is the situation that we're considering. So there's no arrow of time in the probability distribution as yet, right? If we wanted to do causal analysis on this situation, we would draw a little causal network. I don't know why I'm not, oh yeah, I know why. Come on, here we go. Here's a causal network, very, very simple one. Again, we're not going to need a lot of advanced level concepts as far as causality is concerned. Swinging my arm, glass is falling, wine on the floor. And we're going to ask the question, does knocking over the glass cause the wine to spill onto the floor? Yes, the answer is yes. I'm not holding you in suspense, okay? That is the correct answer, but we're going to think about it really carefully. And you know what I'm going to talk about. There is this idea of the do operator, introduced by Judea Pearl. And the idea is that you can ask whether or not this particular fact that the glass is being knocked over or not is what is causally responsible for there being wine on the floor. And you ask it by intervening and doing this do operator acting on the y variable. So basically you break the connection between what is called the parent. If you had these arrows pointing from one node to another, this is the parent of x is the parent of y because an arrow points from x to y. So you break that connection. So you say, forget about the fact that in the real world, if I swing my arm, the wine glass falls. If I don't, I don't. Just say whatever my arm was doing, who cares, doesn't matter, but I'm going to let the wine glass either fall or not. And then subsequent to that, I will let the ordinary laws of physics do whatever they do. So this do operator says that there's no correlation anymore between x and y, but y can either be yes, the wine glass falls, or no, it doesn't. And we let it do its influence on z. And what Pearl says is that you can say that y is exerting a causal influence on z if in this do operator, if you do one variable, one value, so you say that the glass did fall over. If I find there is a correlation, so the glass falling over changes the probability distribution of the wine being on the floor, then there is a causal influence, okay? So the thing you're trying to get rid of are these correlations caused by something else. If you notice that every time you go outside, if it's sunny outside, So there's no rain and no one has an umbrella up. If it's raining and everyone has their umbrella up. Or is the umbrella causing the rain? So the do operator says, no, I can go in there and just force someone to put their umbrella up and I see that it does not start raining. So this is how to disentangle these correlations. The thing about the do operator is that you can't actually calculate its action just from the original probability distribution, because the original probability distribution has a lockstep relationship between me swinging my arm and the wine glass falling. Yes?
I think there's a typo, you want P of X, Y, Z.
I can't hear you with the math, sorry.
There should be a Y in the numerator. It should be P of X, Y, Z.
That's very possibly true. It could be a typo. I'm sorry, I need to look it up. I don't have that in my brain. Yeah, thank you. So for those of you who don't know, I have a podcast called Mindscape, and I've recently interviewed Judea Pearl for the podcast. It has not yet been published, so I'm letting you in on this information. And Pearl says, this is why statisticians get irritated by the do operator, because you can't figure out its action just from knowing the data that are implied by this actual probability distribution. You have to either do some extra experiments that are outside your original data set, or use your brain somehow, right? Do thought experiments or something like that. And the reason why that is, from the philosophical point of view, is that causality by its nature is a counterfactual notion. It is saying something like, if X had not happened, then Y would have not happened, or something like that. But X did happen, so what do you mean by this counterfactual statement? The do operator is a way to sort of put quantitative meat on those counterfactual bones by saying, this is what we mean by making these statements about worlds that did not happen. What you have to buy into to let that happen is to break the connection between X and Y, so to break the laws of physics, if you want. In the real world, if I swing my arm, the wine glass is going to fall. I'm assuming I'm swinging it in exactly that place. And if I don't swing it, it won't. In this world, in this discussion, we have to imagine worlds where I swing my arm, but it just bounces harmlessly off the wine glass, or I don't swing my arm and the wine glass just hops off the table. Okay, that's what we're assuming counterfactually is allowed in this discussion. It's perfectly okay to do that, because after that, you let the laws of physics do what they do, and that's what you're asking questions about. Okay, so you all knew that. Most of you knew that. There might be some interlopers here, but the causality people knew all that. Here's the point. Again, the probability distribution that is in the actual data has no arrow of time. If you know whether I swung my arm or not, you know whether the wine's on the floor, and vice versa, just as well. Therefore, you might be tempted to ask, is it possible that the fact that causes always precede effects in time is just a convention? Is it just a convenient way for us to think, given other things about the world? Or could we have just as well drawn a causal network with the arrows going the other way? I mean, the probability distribution is the same. So can you just draw it going this way just as well? And the answer is no, you can't do that. There are good reasons to draw the arrows going this way. And the reasons are because the reasons are not due to the initial probability distribution. The reasons have to do with those counterfactual statements that come into defining the do operator, okay? In these other possible worlds that we're comparing our actual world to, there is an arrow of time that is going to matter. And that's what I want to sort of explain. How do we explain that? Well, we have this thing called entropy, which is going to explain the arrow of time. So other people in the room are too familiar with this, but maybe some of you haven't seen it. This is Ludwig Boltzmann. This is his gravestone in Vienna. He has an equation on his gravestone. I always tell my graduate students, what is the equation that will be on your gravestone someday? Boltzmann never wrote this equation down. That's even better. This was written down by Planck. He was trying to translate things Boltzmann had said. But it's a worthy equation to have on your gravestone because it is the relationship between entropy, which was invented as a concept in the early 19th century, and microscopic physics, in this case, in the theory of atoms and molecules. Okay, when entropy was invented, physicists didn't believe in atoms. They couldn't see them. Even when Boltzmann was at the peak of his success, he had colleagues like Ernst Mach who didn't believe in atoms because as a philosophical stance, they said that atoms were an unfalsifiable, unobservable hypothesis and should not be allowed in discussions of science. Happily, we don't have discussions like that anymore in cosmology. But back in the day, your philosophical stances could influence what you thought. Boltzmann was convinced that there was atoms, and he knew about the second law of thermodynamics. So he wanted to say, not just as a fact that entropy increased, he wanted to derive it. He wanted to explain why entropy increased, and he could do that by defining what entropy is in terms of the microscopic theory of atoms and particles. So what he said was, look, if you look at something like an egg, like a cup of coffee with cream mixing in it, like air molecules dispersing through a box of gas, there are things you see. Literally, you're looking at it, you observe certain features of the stuff. You don't see the individual particles, right? You don't see the individual atoms in every single one of them with your eyes. You see some macroscopic features. So we can coarse grain the system. We can define equivalence classes, macro states, which are these regions. This is all the states you can have, the entire space of states. And you can call two states equivalent if they look the same to you macroscopically, okay? So in the cup of coffee, there are many ways to rearrange the specific atoms and molecules that look the same to us macroscopically. And what Boltzmann did is he defined the entropy to be proportional to the logarithm of the number of microstates, specific, exact, full descriptions of the system within the macro state. So why does entropy go up with time? There are two facts you need to know to understand why entropy goes up with time. One is explained by Boltzmann, namely that there are way more ways to be high entropy than to be low entropy. That is in the definition of entropy. Generally, even though it's just a logarithm, generally the volume of macro states corresponding to high entropy states is enormously larger than those in low entropy states. So there are many, many more high entropy microstates. That's one thing you need to know. The other thing is you need to start with a low entropy state. That's trickier. We don't understand that one nearly as well. But if you start in a low entropy state and let it evolve, with overwhelming probability, the entropy will increase over time, just because there are more ways to be high entropy than to be low entropy. If you start with a deck of cards in order and you shuffle them, they will shuffle into some random configuration. If you start in random configuration and shuffle them, they will not order themselves. There are far fewer ways to be ordered than to be disordered. Now, this question of why we start in the low entropy state is the tricky one. So let's imagine that. So what Boltzmann says, in other words, is starting from the universe today, he can predict why tomorrow the entropy will be higher, because there's a lot more ways to be high entropy. What he can't explain is why the entropy was lower yesterday. He wrote about it, and he tried, and he claimed it was all perfectly sensible, and then he gave 4 different possible explanations which were mutually inconsistent. So we didn't quite get the right answer back in the day. But the answer is, why was the entropy lower yesterday than it is today? The answer is because it was even lower the day before yesterday. Why is that true? Because the entropy was even lower the day before that, and it goes all the way back to the Big Bang, 14 billion years ago. So if all you knew was that the entropy today, this is supposed to be today at t equals 500 in this little numerical simulation, if all you knew is the entropy was much lower than 1, where 1 is the maximum entropy of your system, then because the underlying laws are time reversal invariant, you would predict, on average, the same evolution toward the past and the future. So if all you knew was the current macro state and the dynamical laws of physics, you would predict that both the future and the past had higher entropy than today. That is not correct. So you would have gotten it wrong. How do you get it right? You invoke what is called the past hypothesis, which is simply the statement that our universe began in a very low entropy state, okay? Boltzmann didn't talk about that because he didn't know about the Big Bang, et cetera. He could have. There's another possible history of physics where Boltzmann said, you know what, entropy's been going up for a long time. It must have started somewhere. The universe must have started a finite number of years ago. He could have invented the Big Bang before general relativity was invented, but he didn't. No one asked how the sun and other stars could have been shining for an infinite number of years in a finite universe, but they could have. Yes.
So in this physics model, in the slide before this one. Oh
yes.
Thank you. Yeah, in the slide before this one, should I be we're not getting to the formalities, but should I be thinking about states like randomly updating? And that what I'm seeing here is like one run of that update, or maybe like like the average be a behavior of the entropy? I just want to make sure I'm on the same page that there is something random in the way that things are up.
So in the real world, there's not anything random. Like I said, all of the discussion here is going to be perfectly classical. This Mathematica calculation was in fact random. So I put some random numbers in there. What that represents in the real world is just uncertainties about the microscopic data, okay? So in the real world, the apparent randomness comes from the fact that we don't know the exact microstate, but there's no real randomness.
Okay, thank you.
Yeah.
So if it's much harder, my question is about the explanation you gave for this slide. If it's much harder to move from a low entropy state, from a high entropy state to a low entropy state than vice versa, why would you be in an agnostic position if you just see a low entropy state?
I didn't, you slowed down too much there at the end.
Yeah, sorry. I think I said something backwards. So you said you observed that today we're at a relatively low entropy state.
Right.
The arrow of time, the non-existence of an arrow of time in the laws of physics suggests that you should be agnostic about that. You should think that the future and past were both higher entropy because that's more likely. But you had also said previously, explaining Boltzmann's thinking, that it is more difficult to move from a high entropy state to a low entropy state than to move from a low entropy state to a high entropy state. So wouldn't that already suggest that the past was not symmetric to the future?
No, because that statement is also true going from the future to the past. So whatever you conditionalize
I
on.
see.
Yeah.
Yes, thank you.
I'm glad you answered your own question. So, but let me mention in passing, Boltzmann was the first person to invent the multiverse and the anthropic principle for exactly this reason. He knew that if you just picked a random point in the evolution of the universe, you should be at maximum entropy. But you're not, because life cannot exist in a universe of maximum entropy. So he said, maybe we live in a temporary decrease. Boltzmann said, maybe we do live in this point. That's not correct. It doesn't work, but he guessed that. What actually works is that long before now, 14 billion years before now, we were in a very, very low entropy state, okay? So I call this the past hypothesis, that we start in low entropy state. And you might think, if you know a little bit, but not enough cosmology, you might think, well, wait, the early universe was a thermal bath of particles. Isn't that high entropy? No, it is very low entropy because it is gravitationally undisturbed. It's very, very smooth, very, very homogeneous. That turns out, if you run the numbers, to be very, very low entropy. The other question you might ask is, why is it a hypothesis rather than an observation? Don't we make pictures of the early universe and see that it's low entropy? Also, no. What we make pictures of is the radiation field of the cosmic microwave background at our telescopes today, right? We have WMAP and Planck up there in the sky, detecting photons. We extrapolate them backward to make statements about what the early universe was like, under the assumption that the entropy was lower at early times. If we didn't have that assumption, it is overwhelmingly likely that the photons just randomly fluctuated into our telescope and have no relationship to the lumpiness of the early universe. So you need this past hypothesis to make sense of cosmology. So there's a whole nother talk, cosmology-based, trying to explain why the early universe had low entropy. This is not a solved question in cosmology right now. But the claim is that this fact, you started with low entropy, I knew it, all right. Sorry?
We only need it to make sense of cosmology rather than any experiment we ever do.
No, the other way around. We need cosmology to make sense of it. So it is the job of cosmologists to explain why the early universe had low entropy. Once you do that, like you say, you need to make that assumption to do all of science.
I just mean that you could have said the same thing that you said about the photons arriving at WMAP, about any photons arriving and okay, more experiment over there.
Absolutely. The WMAP comment was only to make people understand that we do not have empirical information of the smoothness of the early universe absent a hypothesis of early low entropy. Okay, so what does that get you? How does this increase of entropy explain the arrow of time? So this is the one slide, this is the conceptually important slide for the whole talk. It's trivial to understand, that's the good news, but you better understand it to understand what comes next. So One of the features of the arrow of time is that we have memories of the past and not the future. And I don't mean necessarily memories in your brain. I mean any records, photographs, like we said, okay? Fossils, artifacts. Here is a memory. This is a broken egg. You're walking down the sidewalk, you come across a broken egg lying on the sidewalk. For some reason, you're in a philosophical mood and you ask yourself, what is the future of that egg likely to involve? And the answer is you don't know. There's many possible futures for the egg. It could just sit there for a long time. A rainstorm could wash it away. Dogs could come by and eat it or whatever, right? There's many possible futures. But if you ask yourself, what did the past of that egg most likely involve? You would say, I bet that there used to be an unbroken egg and somebody dropped it, right? It's pretty, you don't know exactly when, et cetera, but the space of possibilities is smaller. Why is that? Why can you say more about the past based on that current data that you have? The answer is not just in the laws of physics. If you have some macroscopic information, which you do, about the present day, and you think that that macroscopic information is compatible with a whole bunch of microstates, and you have deterministic evolution of those microstates, both from the past and toward the future, then the number of possible futures is precisely equal to the number of possible pasts. There's no inequality there. The reason why you can draw conclusions about the past from this that you can't draw from the future is that you also think that we started with a low entropy past. And what you are secretly asking yourself is not just from this egg, what can I say about the past, but conditionalizing on both that egg and the low entropy past. What can I say about the in-between past, the trajectory? So it is not true that in the space of all possible configurations of the universe, given a broken egg, there used to be an unbroken egg with high probability. Given just the broken egg, most of them randomly fluctuated into existence from all the possible molecules in the universe. It's similar, and not right away, not like rapidly. It's just like running the movie you expect for the future, but running it backward, okay? Instead, we think that we came from a low entropy past, and we say that conditionalizing on that low entropy past, how is it most likely to get an egg on the floor or the sidewalk? And the answer is via an unbroken egg. The details take some working out there, but that's the fundamental thing. So you get the point you need to get in your brain is you can't, without that low entropy past, count this as a memory telling you something about a record telling you something about an event that you would conventionally attach with it in the past. Yes.
So I guess, so even if I don't know any physics, which I know very little, I'm still biased to think that the past was an unbroken egg that fell on the ground. Why is it that human brains are biased, have this bias, that the past is low entropy and the...
I mean, you're answering your own question. Every moment of your life, you've been embedded in an arrow of time that is very, very strong. Every sequence of events you've ever seen in time has been one of increasing entropy. You deep in your bones think that entropy just should increase. It is very hard to put yourself in the mindset of someone who doesn't have a past hypothesis to rely on.
So it's a bias of the human brain.
Oh, absolutely.
That made it into physics.
Yeah, so the whole question of why there's an arrow of time in the first place, remember, Aristotle never asked. It's just obvious, right? This is a question that was forced onto us by the introduction of reversible deterministic rules and the invention of classical mechanics. But we also have these statistical facts about initial conditions that bias our feeling for how those deterministic rules show up in the macroscopic world.
My brain evolved in a world with the arrow of time.
But the physics say that the physics is reversible, right? I mean,
the microphysics is reversible. Look, Aristotle says if I have a cup on the table and I push it and I stop pushing it, it stops. He's right, it just stopped, right? But the laws of physics say that the natural state of things is to move at constant velocity. The reconciliation is there's something called friction, and that act of friction, that little sound you hear, increases the entropy of the universe. In the space of all possibilities, without a low entropy initial past, it is equally likely that sound waves will focus in on the cup and push it backward. In the real world, that never happens. Yeah.
Should I think about the probability distribution
I'm sorry, he wants to give you the microphone.
I was just wondering if I should be thinking about the probability distribution of the past states, like when you say the one with the infrared trajectory, is that the one that I think has the highest probability mass? And that's kind of what I'm...
Good. So there is a whole debate in the foundations of statistical mechanics literature as to how to precisely formulate the past hypothesis. Somehow you want to have the highest possible entropy that is compatible with what we actually see. So the past hypothesis is not just the early universe has low entropy. It's that the universe starts in a state of low entropy with the feature that it is not surprising that it evolved into the later universe we see today. And turning those words into a precise statement is an ongoing thing. So what I'm saying is, I don't know, read the literature.
Okay, thank you.
Okay, good. So we want to do this, but we want to do this for causality now, okay? So despite my best intentions, this is taking longer than I thought, so I'm gonna have to speed up a little bit. The setup is to first, we're gonna coarse grain, a la Boltzmann. We're gonna divide our description of a system into macro states and micro variables within those macro states. We're gonna define a probability distribution that evolves over time, starting with a low entropy past. There'll be a crucial input from physics, which is that microvariables, I'll explain this more, but microvariables are faster than macro variables, so they will actually equilibrate faster. There's multi-scales to the dynamics. And as a result of all this, the Markovian property of evolving from one moment to another in the macro world evolves going forward, works going forward in time, but does not work going backward. And that is what is going to prevent us from drawing our arrows backward in the causal diagrams. I'm going to make sense of all this now. So just to convince you that there's work to be done, we're going to have some symbols, some Greek letters. We're imagining a system which is supposed to be the whole universe or anything, pretty big. I'm a cosmologist by training. I talk about the universe. You can talk about the Earth or something smaller, the lab. We're doing classical mechanics. There is a phase space, capital omega, and there is a microstate. There's one actual state of the world, okay? We don't know what it is, though. We have some incomplete information about that. And if you believe in deterministic underlying laws, that state evolves in time in a reversible way. So it's completely deterministic. If you know Q1, then you know Q2 and Q3, but also vice versa. So I cheekily indicated that by putting arrows both sides of the time axis here. Then we're going to coarse grain. So we first divide the whole universe into subsystems. You, me, the lab, the air, all these different subsystems, and each one of them has a microstate. So the whole system can be defined by all these microstates of all the subsystems. And again, at this level, the evolution is still perfectly deterministic, forward and backward. We have not coarse grained yet. I think I slipped when I said that. Now we coarse grain. So this is now you have to slow down a little bit because this is the important part. In each subsystem, this notation is supposed to mean this is a subsystem. So this is like a person or a place or a thing. I don't know, a box of gas, a star, whatever, some part of the universe, okay? And we're going to describe that part of the universe in a coarse-grained way by dividing its coordinates into macroscopically observable facts and other facts, which we'll call the microvariables, okay? So X is the set of macroscopic variables that we need to, it's what we actually see when we look at the system. And then all of the additional things we don't see are encoded in these microvariables Y. Okay, so a very trivial example is the Earth moving around the sun under the force of gravity. The Earth has roughly 10 to the 50th atoms in it, but to predict its motion around the sun, I do not need to tell you the position and velocity of 10 to the 50th atoms. All I need to tell you is the center of mass, position and velocity, 6 numbers, because there's 3 dimensions of space. Okay, so the XAs for the Earth moving around the sun or any other celestial mechanics problem is just center of mass, coordinates, and velocity. And all the YAs are all the relative positions of all the atoms and other things within the Earth, okay? That's one possible coarse graining. There's a whole nother philosophy discussion about why are there certain good coarse grainings and certain bad ones, but that's yet another day. A more common example from the stat mech point of view is, you drop some, I don't know why this looks like a sugar cube, a purple sugar cube into some liquid, but anyway, you drop one substance into another one and it diffuses, okay? So in this description, what we mean by the macro variables XA is the distribution through the vessel of the purple stuff. It starts all concentrated, it spreads out a little bit, it eventually fills the glass. The Y's are the individual positions within that macroscopic set of constraints, okay? So we do that. This is a standard stat-mech move that started with Boltzmann and Maxwell and their friends. And just so as not to be too serious here, there's a fun name that has been given to this called the Mentaculous. This is borrowed from the Coen brothers movie, A Serious Man, where the star of the movie, the protagonist is a physicist who is slightly crazy. He has a brother who is completely crazy, and the brother carries around a book that he calls the Mentaculous, which he says is a probability map of the world. It's a probability of every single thing that happens in the world. Here it is. It looks almost like a causal network. So what we have in our setup is a probability distribution at any one time over the set of all the microstates, which we can divide up into a probability distribution over the macro variables and the micro variables. If we want to, we can just integrate out the micro variables to get a macro probability distribution. And then you can, that's at one time, and you can just use the fundamental laws of physics to evolve it forward or backward equally well. So the only thing I'm saying here is that what you know is that given a state, a microstate, and deterministic underlying laws, you can evolve it forward or backward in time. I'm just saying here, you can do the same for the whole probability distribution, because you just sort of, within the probability distribution, evolve all of the microstates, and you get another probability distribution at other moments in time. So David Albert and Barry Lower have called this set of probabilities at all times the Mentaculous. And they actually got permission from the Coen brothers to do this. And then, so they write papers about deriving emergent phenomena from the Mentaculous. Here is the physics input to my discussion, which I already warned you about, which is that microvariables evolve rapidly. What does that mean? In particular, they equilibrate rapidly. So here's a picture of a system with a medium-sized entropy, mixing cream into coffee, right? So it's not all mixed yet, but it's on the way. So there's some macro distribution, sorry, macro description, a macro state, the XA, X alpha variables. And you can, you've seen this before, right? In your real world, you know how the cream mixes into the coffee. The point I'm making is that at any one moment of time, if you fix the macro state, so you're looking at some particular distribution of where the cream is and where the coffee is, there's all these micro variables, but the molecules are bumping into each other really, really rapidly. So given the constraints of being in that macroscopic configuration, other than that, the microvariables are in their highest entropy state or evolve to their highest entropy state on a very, very short time scale. So to a very, very good approximation at every time, the macrovariables are evolving slowly and we track what they're doing. But within that macro state, the microvariables are in a known distribution, the equilibrium distribution. It might depend on the temperature of the bath they're in and all that stuff, the other variables, but it's a calculable known thing. So even though you can only observe the macro variables, to a very good approximation, you know what the micro variables are, or at least you know what their probability distribution is. There are some mathematical caveats we won't get into, but that's a good way of thinking about it. So what that means is, this looks like the same picture I drew before, but now this is just for macro variables. Okay, so the micro variables, we think we know what their probability distribution is, so we're not going to track them anymore. The point of this plot is, if I tell you the probability distribution of all the different macroscopic configurations the world can be in, that's this moment of time. I don't know if you can see the laser pointer. It's this moment of time, number 2. That's the time variable, okay? And then I could use the underlying laws of physics to evolve it either backward or forward in time. Laws of physics are completely time reversal invariant. And I could build up a master distribution of all of the different things at all moments of time. But I don't do that because I know there was a low entropy past. What I actually do is start with the low entropy past, and I only evolve it toward the future. And then if you want, you can update like a good Bayesian by conditionalizing on observations. What is happening in this big probability distribution is, of course, there's a lot of times when the probabilities describe mutually inconsistent things, right? The volcano erupted or it didn't. And this whole probability distribution includes both. Volcano erupted and it didn't. You could update if you wanted to on the fact that I saw the volcano erupt, but you don't have to. This is kind of like quantum mechanics, but it's not quantum mechanics. There's nothing interfering. There's no complex numbers. It's just a classical probability distribution. Okay. So the important physics fact about this is that the evolution is Markovian. That is to say, since I'm starting at the past in the low entropy state, and I know the microvariable probability distribution, there is a known unique deterministic evolution of this probability distribution forward in time. That's what Markovian means. I can go from one moment in time to the next one. I don't need to keep into account knowledge of the past as well. So to update from moment 2 to moment 3, I don't need to know what moment 1 was doing. I just need to know what moment 2 was doing. And what that means, and that's because the microvariables are sort of just quickly equilibrated. They're not secretly conspiring to do something weird in the future. So there's nothing being set up in the past to surprise you in the future. That's the assumption that we're working under. And it's very physically plausible, and you couldn't do statistical mechanics without it. So it's okay. And so this suggests arrows, right? And it's perfectly okay. These are the correct arrows to draw, going from the conditions of macroscopic systems at one moment of time to the future. This is why it is natural. I haven't shown it's the only thing to do, but it is sensible and natural to draw the arrows to go from the past and the future, because that is the direction in which things are Markovian, right? They're not the other way around. That was the point of the egg example. If all you know is the macro distribution at moment 2, you cannot just use the laws of physics to derive the correct macro distribution at moment 1. You also need to conditionalize on the low entropy past. All right, so I've been using the word entropy a lot. Here's the actual definition of entropy in this land of probability distributions rather than coarse-grainings. Given a probability distribution over some variables, the entropy is minus the integral of the probability times the log of the probability, which, if you recognize it, if you work with these kinds of things, this is just the expectation of 1 over the log of the probability in that probability distribution. So this is sort of a side light, but just so you're clear on what is going on here, you could do this separately for the macro variables and the micro variables. You could define the entropy of the macro variables. What does that mean? Well, you have the volcano. It could erupt or not erupt. So there's some probability distribution over did it erupt. And I could calculate the entropy of that probability distribution. You might say, aha, that entropy should go up with time because there's the second law, and in the past it didn't erupt, but in the future there's uncertainty, so the entropy goes up. That is not right. The macroscopic entropy that you can define here could go up or down. There's no law of physics that says that. In fact, look at what happens here. The purple stuff converges on a single unique distribution, right? We know what the distribution is, the macro variables. The micro variables within that distribution, that's where the second law kicks in. So knowing what the macroscopic configuration is, as the macroscopic configuration changes, the entropy of the associated microscopic variables goes up with time. That's the purple stuff is expanding through the glass. Okay, so that's just, if your friends ask you what is the second law, it has to do with these microscopic variables and their entropy increasing, which is a reminder that there's another thing that you might have said and gotten wrong. And I only say this because I thought it and it was wrong. So you have to teach yourself these things. For the future, with the volcano example in mind or a flipping coin example in mind, right? There are many examples we have of having a system now in some macro state, but not being able to predict what will happen next. Who will win the presidential election? Who will win the NBA championship, et cetera, right? So if you have a probability distribution over all those things, you might imagine that its entropy goes up as its uncertainty increases with time. When you flip a coin, you're in a single macro state, its macro entropy is 0. You flip a coin, it gets 1 bit's worth of macro entropy in the future. But that's not why you draw the arrows in the causal diagram going from the past to the future, because of these diverging dynamics. Number one, there's plenty of deterministic dynamics, even in the macroscopic world. You can predict eclipses in the future and when the sun is going to rise, et cetera, in situations where the entropy increase is not noticeable. But also there are many examples where 2 different states, macro states, converge to the same macro state. So the macro entropy goes down. So in the world of the macro variables, for any given subsystem, the entropy could go up or down or anything. That is not the arrow of time. That is not the reason why we draw our arrows in the causal diagram in that direction. It is, this is just, I can't help but noticing, but talking about this, even though it's not what the talk is about, you'll grant me 2 slides on this. It is related to the origin of complexity in the universe, okay? So if you look at, here's a closed system that's entropy is increasing, cream on the top, coffee on the bottom. These are actually all at the same time, but you can get what I'm trying to represent here. Entropy is increasing from left to right, right? Nope. This is very low entropy, all separated. This is very high entropy, all mixed together. But think about simplicity versus complexity, where I literally mean the amount of information you'd have to give me to describe this image. You could literally take a photograph of it and compress it on a JPEG file, okay? The leftmost image is very simple. All the creams on the top, all the coffees on the bottom. That's a full description with the macro state. The right-hand image is also very simple. They're all mixed together. Even though this was low entropy and high entropy, this is simple and this is simple. And it's in between that things are complex. There's a specific non-trivial mixing pattern, little fractal swirls, etc. And this turns out to be a very common behavior. It's not universal or necessary, but is very allowed. So you can go from low entropy to high entropy, and it's in between that you have the ability to be complex. This is not just cups of coffee. The universe does the same thing. The very early universe was very, very low entropy and very simple. This is a photograph of the very early universe, 1 second after the Big Bang. It's not really a photograph. It's a white rectangle that I tilted in PowerPoint. Okay, there's no photographs of the universe 1 second after the Big Bang, but we know what it looked like. It was very hot and very, very, very smooth. Several 100,000 years later, inhomogeneities had begun to grow under the force of gravity. This is a photograph of the cosmic microwave background a few 100,000 years later. A few tens of billions of years later, this is the current universe with stars and galaxies, and it's very complex. But that complexity is going away. The universe is accelerating. The stars are burning out. They will fall into black holes. Those black holes will evaporate. The last black hole evaporates about a Google years from now. And that is the highest entropy state of the universe, and it is also very simple. So when people say, you know, life is a fight against the increase of entropy, they have it exactly wrong. The only reason life is possible is because entropy is increasing. If entropy weren't increasing, we'd be in thermal equilibrium. There'd be no life around. So life is parasitic upon the fact that entropy increases. That's why complex structures can rise in the universe. Just wanted to let you know. Okay, back to the glass of wine. We can answer this question now very, very easily. We've done all the work, all the setup. It's all trivial now. So the question is, given this probability distribution between my arm swinging, the glass falling, and the wine being on the floor, which is perfectly reversible in time, are we allowed, this is what we usually do. We say if you put the do operator in the middle, you can show that the glass falling causes the wine to be on the floor. And we're asking, is it okay to reverse that? Could we just as well have said that it is the glass falling that caused my arm to move? Or to make it grammatically correct, is the fact that the glass will fall the reason why I am swinging my arm? The answer is no, but we're trying to figure out why. The answer is no. The reason why is because the backwards in time evolution is not Markovian. You can't draw a causal network that the original causal network that you interfered with to put that do operator on there. The actual past distribution in the real world, the Mentaculous, is not derivable just from the current state and the laws of physics. You need to also conditionalize on something in the future of that. And what that means is, in the causal network language, sorry, I'm just repeating myself here. If all we knew, and this is the hard thing to sort of appreciate intuitively because of exactly your question, we're embedded in the arrow of time, and it's hard for us to reason counterfactually. If you didn't know that there was a low entropy past, but you did know that the wine glass was falling over, you would not be able to say, oh, I probably swung my arm, or someone probably knocked it over. In the space of all possible ways the wine glass could fall, most of them are the wine glass just randomly jiggling its molecules and falling over. Now that never happens in the real world because we're coming from a low entropy past. But in the space of all possible things that could happen, that is overwhelmingly what you would predict. Okay. So just from the current macro state, including the fact the wine glass is falling over, you would not retrodict me swinging my arm. You also need the early universe evidence, and that's not in the causal network. That's the point. Here is the good causal network with the arrows pointing from the past to the future. If you tried to say, can I just reverse the arrows? The answer is no. There is a technical definition of when it is okay to draw these arrows in the sense that when is it okay to consider a certain set of variables as the parent of another variable? And the answer is you have to be able to reconstruct the whole graph just from knowing the dependence of every variable on its parents. So you don't need to separately know its dependence on other things. The parents of the variables are all you need to know to reconstruct the whole probability distribution. If I reversed the arrows, that wouldn't be the case. But I could make a graph with reversed arrows, but they would have some arrows that loop around. You would need to have the low entropy past as the parents of everything. So you could not just draw arrows going from the future to the past using the laws of physics. That would give you a mistake because you would predict that entropy would go up as you go from the present to the past. That's wrong. So the answer is that if you want, and maybe you don't, but if you want to draw a causal network where the arrows just go from one moment in time to the next or the previous, the fact that the entropy of the early universe was low implies you will only get the right answer if those arrows are pointing from the past to the future, not the other way around. That's the punchline. So, therefore, I claim the low entropy past is the explanation of the arrow of time. And again, lots of us have been convinced this is correct for a very, very long time. The people who generally think about this kind of question are not also generally up on the most recent thinking about causal networks and things like that. So I think it's a natural kind of synergy to put these two things together and use the causal network analysis to pinpoint why exactly increasing entropy is relevant to the question of why causes precede effects. Now, when I first started working on the question of the arrow of time, why is the past different from the future? Someone asked, slightly wisecracky way, so what's your next project going to be on, the mystery of alphabetical order? The joke being that, look, we all know the past came first and then the future. Like, this is not a thing that we have to worry about, right? Causes precede effects. I was born young, I will grow older. Like, that's not something that requires explanation. I mean, it's a known fact, that is true. I'm not denying that the arrow of time is real, but I do think it is actually very, very valuable to understand why in a way that we mostly do, but not completely. And this kind of work is a step in that direction. It's part of the much bigger project, right? We have, and again, it goes back to the question of why we're so convinced that the arrow of time is just there, that if we see a broken egg, there must have been an unbroken egg, right? We're convinced of that. Why? Because there is what philosophers call the manifest image of the world, the picture of the world that we have just from growing up and moving around in it. Biology and evolution have something to do with it, but also training and experience and learning has something to do with it also. We put together a folk image of the world consisting of tables and chairs and processes like cause-effect relationships. And in that world, if you don't keep pushing the cup, it's going to stop moving. Momentum is not conserved in that world, and that world is very natural and intuitive to us. But science gives us a different image of the world. It says that there's this cup and this table are made of atoms, and the atoms obey reversible laws. And actually, there are things called relativity and quantum mechanics. And the project of connecting those is both intrinsically intellectually interesting, but also will potentially teach us things. So I think that there are many, many, many questions remaining unanswered in this broader project. Again, most of these you have guesses that are probably pretty good, and it's not a matter of completely starting from scratch so much as it is a matter of sharpening up your guesses into formal derivations and careful statements. I divided the world into subsystems halfway through the talk. Who ordered that? Where did that come from? Who says how to divide the macro state or the whole state of the world into a state of subsystems? Why do I not need to know the microscopic theory in order to have a macroscopic understanding of the world? Why was Aristotle able to say something about cups of coffee and so forth without knowing about Newton's laws of motion, right? Why are there emergent and autonomous higher level laws that are independent or at least not requiring knowledge of the lower level laws? Do the different levels that we have influence each other? Is there downward causation? Is the notion of causation a useful notion between levels in addition to being inside of levels? This stuff is very relevant to the origin of life. Why are there complex systems, right? Life is a paradigmatic complex system. Consciousness and the fact that we have self-referential understandings of the world, the relationship between quantum mechanics and classical mechanics, and all these things. Almost everything interesting about the world other than fundamental physics is part of this big project of connecting fundamental physics to the world that we see around us. There's a lot of good low-hanging fruit to be picked in this field. Thank you very much.
Thanks a lot, Sean. Are there any questions in the room or questions on Zoom? Yes.
I was wondering about, there was a shift from, we talk about the microstate of the universe, and then we talk then about the Mentaculous. So we've moved from a microstate to probabilities, which presumably are dependent on our uncertainty, our measurement uncertainty. So that's the question of like, is that the question of setting this microscopic cutoff, I guess?
It's simply a question of the real world, of the fact that there is, the real world is quantum mechanical. So there's a huge thing lurking under all this that I'm not touching on. But in this pretend version of the real world where things are classical, there is a state of the world, a single point in phase space, but we don't know what it is. We have incomplete information about the world. We know where the sun is in the sky. We don't know the location of all of its atoms, okay? So what we do is we invent a probability distribution for our sakes. Given the macroscopic information, what is the probability that we ascribe to all the microscopic variables we don't know? There are some principal reasons for inventing some rather than others, but if you were Laplace's demon, if you knew the microstate of the world, you wouldn't need to do any of this stuff. Laplace's demon doesn't know about entropy or the arrow of time. Laplace's demon just knows the whole world perfectly, but we're not him.
So in particular, we have, if we're speaking probabilistically, meaning not being omniscient, there is some degree of lower entropy past, and how low that needs to be depends on our level of not quite omniscience.
It does, but happily, I know exactly what you're saying, but the dependence is really, really weak. It's pretty clear the best we can do to describe the early universe. It's a plasma of particles with a certain density, with a certain distribution, et cetera, et cetera, et cetera. And given those macroscopic constraints, even if we don't know the precise density at every point in time, we have a very good understanding of what the probability of the density is at different points in space and time. And again, within that macroscopic set of constraints, we have a very good notion of what the micro equilibrium distribution is. So even though in principle, it is dependent on our observational abilities, if you had a very good computer with robot eyeballs, et cetera, it wouldn't do much better than we do. It's pretty robust.
Thank you.
Yes. So if now you take a quantum world, you have the measurement problem and the projection postulate. So is it also a way to explain the arrow of time? Is it a new way? Is it related?
Good. So I knew this would happen. It depends on your favorite version of the foundations of quantum mechanics. My favorite version is the Everettian, or many worlds interpretation of quantum mechanics, in which there is no projection postulate. There is no wave function collapse. There's nothing special called measurement or observation or anything like that. There is only the evolution of the wave function as a whole, according to the Schrödinger equation, forever. And part of that evolution is branching into different possibilities. So you get a picture that is very, very much like this picture, except it's quantum rather than classical. And the different parts describe literally different branches of the wave function of the universe that become real. In the classical world, the different probabilities, like did the volcano erupt or not, one is real and the others are not anymore. In the many worlds, quantum version of it, they're all real with some amplitude. But the same questions arise. Why was, you still need to have a past hypothesis that explains why the quantum wave function of the universe started in such a very particular place? That's a good question.
Thanks for the fascinating talk. So in causal inference, there's this idea or principle of independent mechanisms that postulates that the distribution of causes should be independent in the sense of not sharing information with the mechanism that generates the effects from the causes. And there's some work by Dominic Jansing and colleagues that try to connect this to the thermodynamic arrow of time by postulating that similar independence should apply to the initial state and the dynamics of a system. And under this, you can then show that you actually have some shared information or some dependence between the final state and the reverse dynamics, which is kind of like break this asymmetry. So I'm wondering if you're familiar with this work, or if not, if you have any thoughts on that and how it maybe connects to this past hypothesis or the conditioning on an independent initial state, or maybe that's related to, you know, a low entropy past.
I'm not familiar with it at all. No, I'm surprised I'm not, because I certainly have Googled those words that you used, but there's probably more than one piece of work on it. The latter couple sentences you said don't sound completely convincing to me. Maybe I just don't understand them. I know there was a brief description. I don't think that the introduction of quantum mechanics either helps or hurts the search for an explanation for the low entropy initial condition. There is a whole intellectual project of deriving the arrow of time without a low entropy initial condition, putting some true time asymmetry in somewhere, maybe because of quantum mechanics, okay? I think that's misguided because number one, there is a low entropy past. And number two, once you have a low entropy past, you've explained the arrow of time. So doing anything else to explain the arrow of time, I think is not the right thing to do. So I would say that whether it's quantum or classical at heart, we have the same question. Why did the early universe have low entropy? And that's fundamentally a cosmology question. Without cosmology, you can't answer it. There's no principles of simplicity or symmetry or anything like that. It could have been very high entropy and it just wasn't, and we're not sure why. I'm not sure if that addressed the question.
To some extent.
So you showed us this example where the entropy increases in the coffee, but the complexity goes up and then goes down. And you were saying, oh, think about a JPEG, you know, how it'd be easier to like store this one and harder to store the one in the middle.
Exactly.
But that kind of depends on the basis that I'm like viewing it in. And so if I have a different basis, maybe it's an unnatural, maybe there's a natural basis for us. And for us, the one in the middle is the most complex one. And so it really depends on your perspective. And my question is, you know, why should it not be the case? Like I'm wondering, so the case for entropy here always going up has been, as you said, I've always seen it going up. But is there a way for me to know that that's not based on my viewpoint? Like, is there a different basis I could have? It's just kind of a vague, fuzzy kind of question. But is there a different basis that I could have in which entropy doesn't go up or down or do weird things?
It's not a very vague, fuzzy question at all. It's a very common question. And I know the answer. Sometimes people believe me when I tell it to them and sometimes they don't. So it's related to the question that was already asked. There is a coarse graining that we put on the microstates of the universe following Boltzmann, okay? And he says, look, here's the coarse graining, here's a typical path. Do a different coarse graining, right? Imagine I just take this little tiny ellipse and I move it down there. And I move the medium-sized ellipse down there. Then I could find that the same trajectory of the universe is now one in which entropy is decreasing. Not all coarse grainings are created equal. There are right ones. And the right ones are not fixed by arbitrary choices. They're fixed by the laws of physics. When you look with your eyes at the cup of coffee, all that's physics, right? There's no version of a detector which would let you see all the atoms in that cup of coffee, because there's no photons coming to you from the atoms in the middle, et cetera, right? You have access to certain wavelengths. It gives you certain information. That's what gives us the coarse graining. And Robbie the robot would make the same coarse graining as you would.
Awesome, thanks.
A whole bunch of questions from Zoom,
All
so
right.
I'll have to
The internet has
we'll
questions.
just do a couple. So from Tom Lengauer, is here an approach to arguments explaining the past hypothesis, or will we just have to resort to the anthropic principle?
Oh, some of us have theories to explain the past hypothesis. I think, again, that's another talk. It's not this talk. I think it's perfectly legitimate for 98% of science to say the early universe just had a low entropy and we conditionalize on that for literally everything we do. But 2% of us need to be thinking hard about why the early universe had low entropy without cheating. There's plenty of papers that have been written on this. It's probably like the biggest set of the fraction of papers that are just fundamentally misguided from the start. I don't know why I'm looking at you. I should look at the camera, I guess. The rules of the game are you have to explain why the early universe had low entropy without assuming anything that by assumption distinguishes the early universe from the late universe. So in the picture, this is already a very anthropocentric picture because this is from the early universe to today. But guess what? The universe doesn't end, it keeps going, right? So we're in the middle of this, not at the end of it. But people make arguments like, well, the early universe state we need to start is especially simple in my model, okay, or whatever. And then it was Hugh Price, the philosopher, who really emphasized, why doesn't your argument apply to the late universe? The late universe is very, very different than the early universe. And if you have some argument for why a certain condition should be the initial condition, either it also applies to the final condition, or you're just smuggling in the asymmetry. So that's the challenge. The solution that has been proposed by myself and my collaborators is that the early universe that we call the beginning is not the beginning. It is just one moment that came from a pre-existing universe. And if you look at the whole shebang, if you go toward the far, far, far past before the Big Bang, the arrow of time is going the other way. There's a moment of time in the middle with the minimum entropy, not a minimum, the lowest entropy the universe ever had, but not necessarily low. And it increases in both directions from that. But to make that work physically, cosmologically, you really need to wave your hands pretty fast. And I would not say that we're anywhere close to having a consensus on what the right theory is.
I'll ask one more. There are a lot here, but so just one more. From Carlos Gerardo. So if I understand correctly, your explanation of why we have memories of the past, but not the future, is that macro probability distributions satisfy the Markovian property if we assume the past hypothesis, okay? I'm confused about how to go from the coarse graining to the Markov property. I suspect my confusion comes from the difference between the two definitions of entropy you used.
Excuse me, sorry. It doesn't. That's not where your confusion comes from. You only need the definition I gave for what I call the macro entropy is never used as the entropy of anything by anyone but this talk. I was just trying to sort of preempt the possible confusion about the possible diverging dynamics when you flip coins or have volcanoes explode or whatever. The point is that if all you had was a condition at one time and the laws of physics, all of your extrapolations statistically about the past and future had better be equal in terms of entropy or anything like that. You should have no extra leverage over the past or the future if all you have is the dynamics. And we do think we have extra leverage over the past. We have memories and records of it that we don't have over the future. I'm not sure that's answering the question. Was that answering the question?
No.
Can you just try it one more time? Can you just ask it one more time? Is it still there?
I'll read you the question again. So
I don't want to ignore it.
Your explanation of why we have memories of the past but not the future is that macro probability distributions satisfy the Markovian property if we assume the past hypothesis. Okay, I'm confused about how to go from the coarse graining to the Markov property.
So okay, good. Yeah. You need that extra bit of what I call the local equilibration hypothesis, right? So yeah. So the point is that, yeah, what is the point? Well, how can I best say this? Here would be the macro distribution through time if I didn't have the past hypothesis, okay? This is some set of random variables describing the states of different subsystems, the macroscopic subsystems. Here's a cup, here's a table, here's a volcano or whatever, okay? That's X1, X2, X3. And at moment 2, someone tells me what that distribution is. I can use my knowledge of what the microvariables are, not their states, but I know what the total set of microvariables is, I'm assuming. And the local equilibration hypothesis tells me I know their probability distribution, right? So given the macro probability distribution, that's all the knowledge that I have or need, and I can use the laws of physics to evolve it in both directions, either way. But if I did, the entropy of the individual systems, the microscopic entropy, so I have some macroscopic configuration and I calculate the entropy of the microvariables within that, all the atoms in the cup of coffee and milk, for example, it would go up in both directions and it would be perfectly Markovian in both directions. But that's not the real world. That's not what the world does. That would be a world where today, this moment in time was the lowest entropy moment the universe ever had. And entropy would increase in both directions. We need a universe where the entropy was lower in the past. So we have some extra hypothesis. And it's not that this allows Markovian evolution. It's that it doesn't allow it toward the past. It says that the Markovian evolution only works if you start with the past hypothesis and work toward the future. If you started at some intermediate time, the evolution to the past is not Markovian because you need to conditionalize over some future goal. Not future, but you know what I mean, the past goal or whatever you want to call it. So it's that extra boundary condition that ruins your attempt to reverse the arrows.
I think we are already over time, but I guess we will take one more question, maybe from the room.
Please apologize me. The question will be more connected with the assumption of the two arrows in the Big Bang than the causality, but I really like it as an assumption. So I'm trying to understand. So you say one assumption is that in the Big Bang, I have two splits, two directions of time. And the second one is a universe that we do not observe at all, where at the same time, if we observe it, we would see a universe where from our perspective, we will see that the effects cause the causes, but for their universe, it is again normal, the causes cause the effects. I would like just one more comment about that because I found it really interesting.
So it's not that the Big Bang is the moment of lowest entropy. It's that there was a moment of lowest entropy. So here's a version of this picture, but now time is going vertically. I'm taking this from a different talk. So here is an empty universe, okay? There's nothing going on. There's no matter, no galaxies or whatever. So there's no arrow of time at this moment, except what the previous 30 slides in this talk talked about is that there is quantum mechanics and there is gravity, okay? So there is quantum mechanical fluctuations in the curvature of space-time itself. And those fluctuations can give birth to a little baby universe that pinches off and goes its own way. And that, yeah, here's a picture. No one has ever taken a picture of this. This is just a computer simulation, but you know what I mean. Okay, so the point is that we're presuming that even though there was this universe that was empty and quiet, and we thought it was as high entropy as it could be, so it's just equilibrium, it would stay there forever. In fact, there's this very unlikely but possible quantum fluctuation that gives birth to a little baby universe. And we have eternity to wait. So in fact, even though it's rare, it will happen an infinite number of times as you go in time away from this moment. And most of these little baby universes will just collapse in on themselves and be stillborn. But if they have exactly the right initial conditions, they will puff up and be a universe just like ours. And the process to go from that little tiny universe to puff up and be just like ours has a very pronounced arrow of time until it equilibrates and empties out, which will happen to us about a googol years from now. All of that story can also be told going toward the past because the underlying laws of physics don't know the difference between past and future. And there could even be baby universes at the same time as this. Doesn't matter. You can include them if you want. The point is, if you wait long enough, all these individual universes will keep popping into existence, more and more of them, and the entropy of the ensemble increases without bound. So the entropy at any one moment is finite, but there is no upper bound on it. It can always increase. And that happens infinitely far to the future, infinitely far to the past. In each one of these little babies, there's a local arrow of time. From the global point of view that no observer has, these arrows are pointed in the opposite direction to these arrows. So it's not that these people would say effects precede causes. They would say we live in the past. And we say that they live in the past. Perfect place to end. Thank you very much.
Thank you.
Reminds me of the have a comment.